So, what do the AI on your phone, a high-tech medical scanner, and Einstein's theory of space-time all have in common? Well, it turns out they all lean on one single, incredibly powerful mathematical idea, the tensor. Now, I know, that word sounds pretty intimidating, but stick with me. By the end of this, you'll see how this one concept is like a universal language for describing our world.
To really wrap our heads around what a tensor is, let's start with something we all know, a spreadsheet. You know, rows and columns, great for organizing basic data. But what happens when your data gets more complicated than that? What's the next step up?
You can think of it like climbing a ladder of complexity, or what we call dimensions. Okay, so at the bottom, a single number, say the price of a coffee. That's a scalar. It has 0 dimensions. Now, a list of those coffee prices for a whole week? That's a one-dimensional vector. A grid of prices from different stores over different days, that's a two-dimensional matrix, which is, your classic spreadsheet. So a tensor is just the very next logical step. It's a data structure with 3, 4, or even hundreds of dimensions. The best way to picture it, just imagine stacking a whole bunch of spreadsheets on top of each other. Okay, so if a tensor is just a bigger box for numbers, what's all the fuss about? Why are scientists and engineers so obsessed with moving beyond the good old spreadsheet? Well, to get that, we need to look at what makes a tensor so much more than just a multidimensional list.
And here it is, the core idea. A tensor isn't just about holding data. It's about holding structured data. It's built from the ground up to handle the complicated relationships between all those numbers. That's exactly why it's become such a fundamental tool in so many different fields.
And this is where it gets kind of mind-blowing. The exact same mathematical object can describe the ridiculously complex web of connections inside an AI's brain, and it can describe how space-time itself bends in curves in Einstein's theory of general relativity. Tensors are the hidden language for both.
So, what's the secret sauce? What gives tensors this incredible power? It really all comes down to one single core property that sets them apart from just a plain old list of numbers.
This right here is the magic trick. A tensor describes a physical reality, let's say the force of gravity or the flow of heat. That reality doesn't change just because you change your point of view, right? It's still the same physical thing. The numbers inside the tensor might change if you switch from, say, meters to feet, but they change in a perfectly predictable, systematic way that keeps the underlying physical law totally consistent.
Now, this transformation behavior, it comes in two main flavors. You've got covariant tensors, which transform with the coordinate system. Think about a slope on a map. If you stretch the map, the numbers describing the slope have to stretch with it. Then you have contravariant tensors, which do the opposite. They transform inversely. Velocity is a great example. If you switch from miles per hour to kilometers per hour, the number for your speed has to change to make sure you're still describing the exact same real-world speed. Okay, so you have this massive, ridiculously complex tensor with millions, maybe billions of numbers. How on earth do you find the important patterns hidden inside? Well, scientists use a method called decomposition. It's kind of like taking apart a complex engine to see its core components, or breaking down a fancy recipe into its basic ingredients to understand how it works.
And there are 3 popular ways to do this. First up is CP decomposition, which is fantastic for finding the simplest, most fundamental building blocks of the data. Then you've got Tucker decomposition, which is a bit more flexible and pulls out a central core of the information. And for the really, really big stuff, there's tensor train, a beast of a method that's designed to tackle the super high-dimensional data you see in areas like quantum physics.
All right, so this is way more than just abstract math. These tools are humming away in the background, powering some of the most advanced tech we use every single day. Let's take a look at where they're making the biggest splash.
Yeah, as you can see, tensors are not a niche tool anymore. Not at all. They're absolutely everywhere in machine learning, and they're still fundamental to modern physics. But look at this. They're also driving major breakthroughs in medicine and in the race to build a quantum computer. Let's dive into a few of these.
Think about an AI that generates an image from text. To that AI, every image is a 3D tensor. It has one dimension for the image's height, one for the width, and a third one for the color data, the red, green, and blue values for every single pixel.
Literally all the learning that happens inside that AI is just one massive series of tensor calculations.
This is incredible. In medicine, there's a special type of MRI that uses tensors to track how water molecules move around inside your brain. Because water moves differently along the brain's neural pathways, doctors can use this data to create these stunningly detailed maps of the brain's wiring. This helps them diagnose diseases like multiple sclerosis or see how a patient is recovering from a stroke.
So trying to simulate a quantum system on a normal computer is basically impossible. Why? Because the amount of information you need just explodes with every single particle you add. Tensor networks are this brilliant workaround that lets researchers represent and calculate these insanely complex quantum states in a manageable way. They're an absolutely critical tool for designing the quantum computers of tomorrow.
And of course, all this real-world magic is powered by a whole ecosystem of programming tools. For machine learning, Python is the undisputed king, with its famous libraries like PyTorch and TensorFlow. But for other jobs, languages like Julia, Rust, and C++ offer specialized tools when you need raw speed or maximum safety. Okay, so tensors have already come so far. Where do we go from here? Well, all the research is pointing towards a future that is even faster, smarter, and way more multidimensional.
Progress is really speeding up on three main fronts. First, we're building custom hardware, like Google's Tensor Processing Units, or TPUs, that are designed to do one thing and one thing only: lightning-fast tensor math. We're also writing smarter software that can automatically optimize these huge calculations. And we're inventing entirely new algorithms to pull even more insights out of all this data.
Looking even further out, researchers are tackling some huge challenges. They're trying to standardize tools to make all this easier for everyone to use. They're also figuring out better ways to handle what are called sparse tensors, data that's mostly just empty zeros. But maybe the most exciting frontier is integrating tensor calculus directly into AI, which could unlock a whole new generation of machine learning models that are more powerful than anything we have today.
So from a simple spreadsheet, we've traveled all the way to the absolute cutting edge of science. From color images to brain scans to the very fabric of space-time, our world is just full of these complex, multidimensional relationships. And tensors give us a language to finally describe that complexity. As we generate more and more data, it really makes you wonder, are we heading towards a future where everything from the tiniest particle to the biggest galaxy is ultimately understood through the lens of a tensor?